If my sensor is no good, how can I feedback? Not good. Doesn't matter how good your method is. So feedback system, first of all, you gotta make sure your measurement devices are good. That's the first job you have to make sure that's good. Because you need to depend on that to feedback. Your measurement device is broken, then how can you feedback? You can't. Because your observer is no good. Your observer requires this output here. Think about it. Your observer requires this output. If this output is not good, it's not noisy, you don't expect your estimate stay that good, right? No. So you can't just depend on the method I teach you here. You have to make sure your device is all good. Your actuator is good, your sensor is good, your sensor is good first. Then you also make sure your actuator is good, because the actuator provides you the power. You need the certain power. For example, you compute the force. You compute the force here. That's the force. This is the force, feedback force. You compute this force. But this force is, if this force exceeds the maximum power that this actuator can provide, then what happens? You don't have the desired performance, right? So, sometimes you have to try many different designs such that you don't want to exceed the maximum force that your actuator can provide. Understand? Although now I give you all the kind of technique here. When you design observer and design pole, now make sure that your observer poles are more stable than closed loop pole. That's the rule of thumb. To avoid some of the problem from the sensors. But in theory, if you have no noise, doesn't matter, this doesn't matter. It's still stable. It won't drive you unstable. It will be slowly stable. It will be slowly stable. Okay. Now we have this very simple case to discuss about the displacement feedback, and we also discuss a simple example to do that. Then we need to talk about the real multiple degree freedoms. We talk about 1 degree freedom, 2 states. And how can we generalize this concept to the multiple degree freedoms? All right, that's what I'm going to talk about here, because this allows you to program it and allow you to have only 1 sensors, then 1 actuators, then you have 100 states or 200 states. You can still design the controller for yourself. Also, you have 2 states, then you have 2 inputs and 3 outputs. You can do it too. So we call multiple input, multiple output methods. The open loop, see, this is only, I'm talking about the continuous time, x dot equal to ACX plus BCU. And AC can be 100 by 100, can be 200 by 100, and then well, it has to be square. So it can be 200 by 200 or 1000 by 1000. BC can be 1 input, 2 input, 3 input, that's up to whatever you have. So the first state feedback means U equal to FCX. Now, if U is a single input, then FC will be only one row, just like what we learned here. If U is 2 input, then we have FC will be 2 by maybe 100. that's state, if state is 100 by 1. So this is very general. Closed loop system is equal to x dot equal to ACX plus we insert the U into the first equation here. We insert U into the first equation here. Then we got this ACX plus BC FCX equal to AC plus BC FCX. Now, from here, from this point on, we are going to make good use of the matrix theory. The matrix theory here is we can make good use of it. And that, all right, now assume we have the closed loop system here, and then the x equal to that. This is just simple the phi k e lambda kt, and lambda k is kth closed loop eigenvalues, and this phi k, that's kth closed loop eigenvector. All right. Now we have eigenvalue and eigenvector problem here. That means if we solve AC plus BC FC, now we can solve the eigenvalue of this closed loop. The closed loop, the eigenvalue means the eigenvalue of, all right, let me just give you some of this idea here. What do we mean closed loop eigenvalue? That's also most people call the pause. All right, the closed loop eigenvalue that means the of AC plus BCFC. So that matrix, the closed eigenvalue of AC plus BC, well, that's what we call the closed eigenvalue. The eigenvalue of AC plus BCFC are the closed loop eigenvalues. So, in here, now the eigenvalue, we have eigenvalue AC plus BC FC, then times this phi k equal to lambda k times phi k. That's the eigenvalue problem, right? So I think in the next, that's what we have here. So that's the eigenvalue problem. All right, this is the eigenvalue problem here. I'll show you here. All right, and well, it's shown here that the so that means we have here, that means AC minus lambda k I plus BC FC times phi k equal to a zero matrix. That's 0 n by 1. So this is zero vectors. This is vector. This is n by 1 vector if assume AC is n by n. So that's n by n matrix. If AC is n by n matrix, then this is n by n. This is I is n by n vector, the identity matrix. And this is n by R. That means we have R input, and this is R by n. All right, that's the dimensions. Let's take 10 minutes off. Not reaching 7.